Welcome back to another session of ECE 441A. This is a session that will look at a particular example of designing a phase lag controller using the frequency response or the Bode plot. Our system is a third order system. It's type 1. It has a numerator with an unspecified gain parameter K. We'll need to determine what that is. But then we have a pole at the origin, consequently our type 1 system. It looks like we have a time constant of 0.1, which gives us another pole at -10, and a time constant of 0.05, which if we look at the reciprocal of that will give us our third pole at -20. We have a three-pole system, no zeros, and an yet to be determined gain in our numerator K, or a gain constant. For that particular system, we have decided that we have the following two design specifications. We have a steady state error specification due to a unit ramp, which is, we want that to be less than or equal to 1/30. And so we have 30s going on in a lot of places. We also want a phase margin of the compensated system or the resulting system to be greater than or equal to 30 degrees. Let's now look at the procedure or walk through the step-by-step procedure that we have introduced in class to design a phase lag controller for this system. The first thing that we need to do before we can even sketch the Bode plot is specify the gain K so that we now have a G of S that we would be able to sketch or draw the Bode plot diagram. In finding K, we are going to then find K from the steady state error spec. And the steady state error spec says that we want that to be, well, we know the steady state error for a type 1 system with a unit ramp is 1/K sub V, and we want that to be less than or equal to 1/30. So now we're saying that we want K sub V to be bigger than or equal to 30. And K sub V relative to our particular system is the limit as S goes to 0 of S G of S, which is now the limit as S goes to 0 of S, 10K over S, 0.1 S plus 1, 0.05 S plus 1. We have the S's canceling. When we let S go to 0, the denominator just becomes 1, and we're left with our velocity gain constant equaling 10K. Let's just go ahead and look at barely satisfying our design spec. So let's make that equal 30, which we wanted K sub V to be, bigger than or equal to. Or now we're saying let's go ahead and solve for K, or K is now in our original plant that we started with. We now know that K is going to be 3. That's the very first step in our design procedure, is finding the gain in our system if it's not yet specified. In this case it was not, and we can use that to adjust the low frequency behavior to satisfy our steady state error spec. In step 2, what we want to do is now plot the Bode plot for our now more fully defined system. That's 10 times K, or 3, and then we have S, 0.1 S plus 1, and 0.05 S plus 1. To put this into Matlab, I'm going to go ahead and create a second order first factor in the denominator so that I now have 0.1 S squared plus S plus 0 and then times 0.05, which I will now define the numerator to be 30 and the denominator to be a convolution of those two polynomials, which are 0.110 and 0.051, and that will then give me a Bode plot. If I illustrate that via Matlab, I've defined the numerator to be 30, the denominator to be that convolution. I forgot that my denominator was just a polynomial and not a transfer function, so trying to put that into the poles function didn't make any sense, which Matlab told me. So I used the roots command to basically check that I had created or built my denominator polynomial correctly. My denominator polynomial has roots at 0, minus 10, and minus 20, which is correct. I can then build up my transfer function with the TF function. That gives me my open loop transfer function for g of s with k defined to be equal to 3. And I then sketched or plotted that, and the resulting figure was produced. I then copied that figure with this edit command. I simply went down and copied it, and then I pasted it into where I wanted it to be inside note OneNote. And now that I have this, my next step in the process is to actually identify my gain crossover to try to see, does my uncompensated system, by just selecting the gain, does that satisfy my phase margin specification of a phase margin of 30 degrees or better? Now I need to identify my gain crossover frequency. Here is 0 dB. I look at where that blue magnitude curve crosses the 0 dB line, and that's now my gain crossover value. I'm going to just sort of assume that that's about 14 radians per second. And if I go down to the same location, I'm looking for how much more phase can I introduce and before I reach minus 180 degrees, and it looks like I'm almost right at minus 180 degrees. So my third step in the process is to identify the gain crossover frequency of the uncompensated system, which I might refer to as omega G or omega sub C. That, I said, is roughly this 14 radians per second. I look and I'm saying that my uncompensated phase margin is approximately 0 degrees. That's not greater than or equal to 30. So now I need to say, well, I need to produce or introduce a phase lag controller in order to achieve that phase margin, since I'm okay to slow down my system response. Now I'm going to be looking for a frequency at which I can achieve or find an angle that is more positive than minus 180 by this phase margin desired plus a safety factor or a safety margin, which I'm saying now I'm looking to find a numerical value in angle that is 35 degrees less than minus 180. So now I want minus 180 plus 35, or I'm now looking at basically an angle of minus 145. But that's not so easy to find on this curve, so why don't I just sort of, well, what I'm saying is I would like to find a frequency where my phase curve is minus 145. In terms of this diagram, let me go ahead and paste it in again. Now I would try to find 145 minus 145 degrees, which is somewhere between those two grid locations. It's easier for me to eyeball the frequency where I cross minus 135. So I'm going to just pick that. That's going to be a bigger safety margin than I needed. My minus 145 is going to be somewhere in there, but that's a little bit challenging for me to locate, so I'm not even going to do it. Let me just look at this particular frequency value, and I'm going to say that that's excuse me, I apologize for that. I couldn't get my pen or cursor over the record button quick enough, so I apologize for that sneeze. Hopefully you didn't have your volume up too loud. But now that particular frequency where I'm crossing minus 135 is 1, 2, 3, 4, 5. It's between 5 and 6 radians per second, and I'm going to say it's at about 5.8 radians per second. So I was really trying to look at the phase curve. This was the thought process, and find a frequency that is close to minus 145 degrees. But I said that was a little bit tedious for me to try to eyeball minus 145 somewhere 10 degrees below minus 135. So I actually just found my omega sub c prime closer to minus 135 degrees, which is really saying that now if I've identified that, my omega sub c prime is 5.8 radians per second, and that really corresponds effectively to a safety margin of about 15 degrees instead of 5 degrees. So I should, with my controller that I design, I hope that I can get better than a phase margin of 30 degrees. Once I've identified my omega sub c, my new gain crossover frequency, that's the frequency that will allow my phase curve to be near this minus 135. What I now want to do is locate my zero a decade to the left or lower than that new gain crossover frequency. Or I'm now going to locate my zero at a value of z equal to 0.58 radians per second. That's part of my controller design. Now what I want to do is find the pole location that will allow me to finish my controller design. What I need to do now is go back to my diagram, and I now have a frequency identified that's between 5 and 6, and I go up here and I say I now need that much attenuation in my magnitude in order to get my gain curve to cross 0 dB at that new frequency. Or to create this new gain crossover frequency, I need to drop my gain or introduce some attenuation. And if I look at that value, that little red mark doesn't look very long, but in between the grid labels, that's 50 dB. So I'm assuming that I'm a little bit shy of a third of the distance between 0 and 50. So I'm saying that, let me just assume now that I need 15 dB of attenuation, or a minus 15 dB is what I need to introduce. To create omega sub c, we need minus 15 dB of gain, or what I've been calling my attenuation. So once I've found that, now I can say that is going to produce my pole zero separation, which is governed or identified by the parameter alpha. I need that to be this minus 15. I can now take the anti-log of both sides after dividing both sides by minus 20. I have log of alpha is now minus 15 over minus 20, so that now alpha is 10 raised to the minus 15 over minus 20, which is 5.623. My pole now needs to be separated from my 0 by a factor of alpha. Step 7 now says P is Z divided by alpha. Z again was determined in a previous step to be 0.58. Alpha is 5.623, so that now my pole is at 0.103 radians per second. I can now use that information to design my controller. I now know that my G of S is 1 plus S over Z over 1 plus S over P, where my Z was 0.58 and my P is 0.103. In terms of Matlab, I will be entering this from higher powers of S down to the constant, so I really have 1 over 0.58 times S plus 1, and I have 1 over 0.103 times S plus 1 in the denominator. Let me now build my controller transfer function in Matlab with those particular numerical values. So that now I can say, okay, well, maybe before I do that, let me just go ahead and look at the stability margin of System 1 and see how poorly I did in terms of estimating the frequency where my original gain crossover frequency occurred. So this is telling me I really have a negative gain margin, and the phase margin is really 0, and it is at 14 radians per second. So I was pretty close to what I was seeing in my diagram. Let me now build up my controller transfer function as a numerator polynomial, which is 1 over 0.58 comma 1, and a denominator polynomial of 1 over 0.103. I believe that was my numbers, comma 1, and that's now my controller transfer function. And I could look at that, I could say, where's the 0 at? And that's at minus 0.58, which is what I had needed for my 0 location. And my pole is at minus 0.103, which is what I wanted to achieve. Let me now combine my controller and my original plant into a loop gain. I will now multiply G sub C times system 1. That's now my new transfer function in the forward path. That's my loop gain. Let me now create a new figure and go ahead and look at the margin associated with that particular compensated system. And now I have a phase margin of 45 degrees. And we didn't worry about the gain margin, but our gain margin now is 14.4 dB. And our phase margin has slid back. I'm sorry, our gain crossover frequency is now lower than it started at. It started at 14 in the uncompensated. We have reduced that down to 4.72, and we've now accomplished our, or met our particular design specs. If I wanted to, I could illustrate or compare the two different frequency responses. I can compare the original uncompensated, let me say that's in blue, with the compensated in red. And there is now how the phase curve gets shaped, and right at the gain crossover that we're after, the blue and the red curve are almost on top of each other, which is what we were trying to preserve. And we have lowered the magnitude curve as indicated by red, the magnitude curve, red curve being below the blue curve. But we were able to satisfy our design specs with this particular controller design, so we can now conclude or stop this design process.